Looks like it's official. Welcome back, everyone. For today's class, we're in a pretty nice spot for ending the course. We're about to finish off chapter 20, and chapter 21 is going to be the last chapter for the entire course. We're probably going to potentially get into one example in there, and then more likely than not, finish it off on the 22nd when we come back on Monday. That means I think we'll be looking into reviewing for the final exam a little bit earlier, since it just makes sense to go into review problems directly after chapter 21. So that's where we're at so far. Any questions or comments at the moment, folks? Okay, well, it's definitely kind of an exciting place to be in the class. We're very nearly done. The final exam will be a take-home exam, like we mentioned, and it's going to be assigned after the review on Wednesday's class. It'll have a 1 week turnaround on the due date, so just like the homework assignments, it'll be due on Wednesday, May 1st. And other things due on Wednesday, May 1st is any late work that you'd like to still work on and get in. I'll still accept them for full credit. So if there was anything that you just didn't get completely finalized or anything like that, then that would be the last day for work, just as the same due date for the final exam, which I guess makes sense. Also, we've got an extra credit opportunity that's open for us. It says here the course evaluations are open until April 26th. So that's going to be Friday of next week, right before finals week. And if you do your course evaluation, the math department really appreciates that kind of data. So, well, they're also required to get it by the State Board of Education. So it's like they have their massive boss requiring it, but it is up to you whether you would like to do it or not. If you do course evaluation for this class, then I'll do this extra credit opportunity here where it says, I will drop one additional homework assignment at the end of the semester. I think we said we're dropping 2 of them, but let me double check before I just say untruths. It's a little different in all of my classes. Our homework assignments are kind of bigger, so I think it was around 2. Let's see here. Yes, we're dropping the lowest 2 assignments just by default for everyone in the class. And if you do the extra credit opportunity, that will update to dropping 1 additional, so 3 in total. To find the course evaluation, I think this is why the math department has trouble. It's not easy to find all the time. You want to click on this little thing. It says open block drawer. Then somewhere on here, not even the first thing, but there it is on the very bottom. So if you click on that, then it has a justification of why it's important. It is up to you, so don't feel like you're being bullied into doing something you don't want to do. If you click on answer questions, I shouldn't do that since I'm not a student in the class. You'll go to a form that should take about 15-ish minutes to complete. Then at the end of that, there'll just be a thank you page that says, thank you for completing the course evaluation. You take a cell phone picture or a screen grab, any kind of screenshot there, send it to my email, then I'll update my book that you've got that extra credit opportunity. Any questions about that so far, folks? Okay, if you've already done the course evaluation, then thank you, that's pretty awesome. You're not going to be excluded from the extra credit. You can still just come right back to, let me see if I can fix this a little bit better. You can come right back to this thing. Let's move it to the top. That might actually help out on getting more hits on this. If you come right back here, if you've completed already, you'll just say you've already completed the course evaluation. Take a screenshot of that, and that works just as well for me. So that's how the extra credit will go. And how to close the block drawer. I guess we could just leave it open. Why not? And I think that's the majority of my announcements so far. Let me close the edit mode on this thing. Any questions at all, folks, so far? Oh, I lost the participants window. There we go. Sorry, not trying to forget the people in Zoom either. Well, we're just about done. And I have a couple other updates here that the choosing statistical method, we're going to go right into this document after finishing out the last problem in chapter 20. It's been updated in a way that's going to help you pick the right statistical method when you're doing the final exam. But we'll look at it a little bit more carefully. And then after that, we'll go into chapter 21. So I think we're ready to begin, folks. Let's take a look where we left off. So this big block of information is about where we were at. The big takeaway points are we're calculating a brand new statistic whenever we're measuring the difference between 2 population proportions, P1 and P2. The test statistic indicates that we're definitely doing that. We're looking at the difference in the statistic values here, but you have to use this statistic for the pooled sample proportion. And confusingly, this statistic right here is not what's used right here for p hat 1, p hat 2. Those are the sample proportion of successes from the two independent populations. The p hat that you see there goes in this location and in this location. So I think that might be a good thing to indicate into the notes right here, that the pooled sample proportion of successes, this thing, which is this new p hat, goes into this location and this location. So that's where you'll use the pooled sample proportion of successes. The conditions are also tricky. I think I misspoke, which was a code word for saying messed up, but I looked at these first. You're looking for the number of successes and failures in both samples to exceed 5 in this particular procedure. If it exceeds 5 in every one of these 4 different counts, then we have a pretty accurate p-value and we can proceed with a great conclusion. If a single one of these fails, then we shouldn't use this method at all. We don't have a large enough sample size. So that's the major takeaways of this. Then calculating the p-value, exactly the same as we've seen before. So I just put down the R syntax mainly. So I think we're just about ready to start off our first problem of the day for this. Any questions at all first about the method? Okay, so jumping down, here's our problem to go along with all this. This one comes from biology, and it's the so-called Trivers-Willard hypothesis. I've never heard about that until doing this problem here, so it was an interesting one for me to read. It says in this hypothesis that it indicates that healthy parents should tend to have more male offspring than female. That's a hypothesis, so I'm not sure why that would be, but they attempt to defend this. It says here that weaker parents should have more female offspring than male. Let's maybe put a page break. Okay, so this is the Trivers-Willard hypothesis that healthy parents should have more male offspring, weaker parents should have more female offspring. Who knows if that's true or not? Here's their justification of why it might be true. They say this tendency may maximize the number of each parent's grandchildren and thus help to ensure that its genetic code is preserved. Since a healthy male offspring can win many mates, but a relatively unhealthy offspring has the best chance of mating if it's female. So that's their justification there. It'll be interesting to see if it plays out in the data or not. But any questions so far with the hypothesis or this piece right here? Okay, it's a pretty long statistical problem, but that's kind of par for the course. They're all big, long, wordy word problems oftentimes, especially the more honest statistical problems. And nothing inside here is giving us a foothold to actually write down information to calculate to anything. It's all just fluff in a certain sense. I shouldn't say that's kind of rude. I mean, it is telling us the context that we're interested in, but nothing that we can analyze really. But here's some good stuff. They say here, in an experiment to examine this hypothesis, a group of 40 opossums were monitored. 20 of them were given an enhanced diet. And they say next, after a certain period of time, the opossums with the enhanced diet had raised 19 male offspring, 14 female offspring. Let's highlight that there. And the opossums without the enhanced diet had raised 15 male offspring and 15 female offspring. Let's see if we can give that one a different color. So there's definitely data there. This is an extra confusing problem, I would say. It said a group of 40 opossums were monitored, but that's not the sample size on this particular problem. What we're analyzing is the number of successes and failures, and it looks like they're indicating here. Let's go with this, having more male offspring than female. We could consider that our success, but it's kind of hard to tell which specifically that would be. Because they wrote their statement right here in the initial statement of the Trivers-Willard hypothesis, I'd probably consider males to be the success, females to be the failures. If they change it around, I would change that around as well. So let's go with that and see what happens. So they gave 40 opossums were used in an experiment. 20 of them were given the enhanced diet. So let's break this up a little bit and say, for the enhanced, what happened there? The possums with the enhanced diet raised 19 male offspring. We can consider that the successes and say X1. One, because this is our first population, the enhanced diet produced, I'll say 19 successes. And the sample size would have been, let's see, 19 male, 14 female. So sample size N1 is going to be 19 plus 14. That sounds like it's going to be, let's see here, 33. So that gets us started on the first diet, or the first group. The other group was the opossums given no enhanced diet, so we could call that a standard diet, I suppose. So for the standard diet, let's see here, it says there were 15 male offspring, 15 female offspring, so X1 would have been 15 successes. The sample size will be the successes, the failures together, so 30 altogether. And I did make a mistake on my subscripts. That is always an easy one for me. Let me make that a little bit bigger. That should have been X2 for the second population. N2 will be a sample size of 30. And these are the data that we're actually going to analyze in this problem. So we have two populations. That means it should be a two sample proportion type of problem. And one thing that's kind of interesting about this already is, if you really want to see if this is a true hypothesis, you might have asked yourself the question, why did they give some of them an enhanced diet, the others a standard diet, and not, say, a reduced diet or something like that? There's a very good reason for that. If you did do that, you are never going to pass an ethics board. You're never probably going to publish your data into any peer-reviewed journal, because these creatures were, these 40 opossums, you do have to treat them nicely. You can't just run an experiment where you're being awful to one group and great to another. So ethics boards are very specific on that kind of stuff. And to talk about that a little bit further, you might have decided, or you might be confused because of this problem. Let's see. The cocaine and the heroin rats, I mean, bad things happen to these rats, and what, for both groups, it looks like we were really abusing those animals. Why would this one pass an ethics board? Well, in this case, if the problem was serious enough that could help with public policy, understanding problems with addiction and such, then these rats would have gone through this, even though it was brutal for them. But the good news about these rats is that rats used in designed and controlled experiments that end up in peer-reviewed journals like this one, they're actually treated extremely nicely until they are up for the experiment. They're all are treated about the same. They're given enhanced diets and all that kind of stuff, because we want to make sure that the differences we see are not the way they were treated initially, but by the controlled and designed experiment right here. So seems kind of unfair, but those 200 rats passed the ethics board and bad things did happen to them. These 40 opossums, we wouldn't even allow them to have a reduced diet right here, because that wouldn't have been necessary to really test this kind of hypothesis. And it doesn't look like it's a type of hypothesis that is really dire. We're not investigating how addiction and things like that are running rampant with heroin, cocaine, fentanyl, etc. So there's no need to put these 40 or 20 opossums through the ringer and be extra cruel in this situation. But that also means that we have potentially less power in the study, because we don't have as stark of a difference between the two groups of opossums. There's always a little bit of give and take when it comes to this kind of stuff. I think that's kind of interesting to look into whenever you're looking at these problems. Sometimes it looks like they're being really cruel in science, and other times it looks like they're being less so. And it's not just because the opossums are bigger animals than rats necessarily. Well, any questions at all, folks, with the initial analysis of this data? Okay, now we're into the describe the parameters portion of the problem. Pretty much the most common feature you see a lot of these statistical problems. And it's so important because these are the things that we're estimating, the unknown parameters, or they are the things that we're going to test in a hypothesis test. So if we don't know exactly what these are, then right down here where we go to give a conclusion, it becomes a massive, massive struggle. But I think at this point, especially after reading over people's exams, I think we are getting good at this. So that's awesome. Congratulations, folks. It's hard to get to this point. Let's write out here, let P1 and P2 denote the true proportion of, it's going to be the true proportion of successes, but we have to hang on a little bit on this one. I think this problem is definitely extra confusing. There were 40 opossums, again, that were split into two groups. That's not the sample size. We're looking at the offspring of these things. So we should say the true proportion of male offspring for opossums given a enhanced diet and regular diet, respectively. So we've got it, folks. That's going to be the parameters in this problem. Any questions or comments to this stage? Okay, next we need some hypotheses. So our null hypothesis that we're going to test is that the Trivers-Willard hypothesis is null, that there's no actual real effect in this population, that no matter how the parents of these opossums were treated, we're getting the same amount of successes. So that's just a statement that P1 and P2 are equal. So here's our null. P1 is equal to P2, or if you prefer, you could write P1 minus P2 equals 0. They're pretty much synonymous. It's more of a stylistic choice of writing these. So that will be our null. We'll test that against the alternative statement. Here we need to be a little bit careful as well. Let's put P1 here, P2 here, and pause for a moment because we've got to decide what is the test. Is it two-tailed? Is it left-tailed? Or is it right-tailed? Anyone see which one it should be? It turns out this one isn't two-tailed, but it's kind of hard to see what the keyword is inside here. This one is either a left-tailed or a right-tailed test. Anyone spot which one it could be, or the keywords that could have indicated it? And no rush, this is a lot of reading to kind of find that. How about someone from Zoom? Anyone spot what the right test should be? Left tail or right tail? Let me double check. I'm actually not sure. Yes, this one looks like a right tail test. And did you see the keywords that might have indicated that? I understand. In fact, when you said right tail, exactly. And that corresponds to right here. The hypothesis indicates that healthy parents, that's enhanced diet for healthy parents, should have more male offspring than female. Let's highlight that in yellow. It didn't seem important at first on the first read through, but again, that's why it's good to read these things multiple times. On the second read through, this stands out a little bit more. Here, P1 is a proportion of male offsprings for the enhanced diet. And so we're thinking P1 should be greater than the proportion of male offspring giving the restricted diet or standard diet in this case. So this one's a right tail test. Let's put that here. Let's also hit it with a yellow highlighter to convey that this is the information that got us right down there. The level of significance is just flat out stated right at 5%, but it doesn't hurt to say it in our own symbols because it's a good reminder. We often use that symbol after we get a p-value. So simply the action of writing it down is putting it in your subconscious for later. So those are the hypotheses to test. Now we have to take a look at the conditions. We've all practically done most of the legwork about that when we broke down the data on this initial analysis. We have to check that the number of successes and failures in both samples exceed 5. Looks like that's the case, but it's not always easy to find in some problems. So let's write it out just to be specific. Also to help out the notes. Let's say here for the enhanced diet, I'll just call this enhanced. The number of successes was the 19 up here. So that means the number of failures would have been 14. And I don't like that comment after all. I often like to put this here, greater than or equal to 5, greater than or equal to 5, only because, again, that's the benchmark in this problem that we had to hit for a large enough sample size. Then do the same thing for the standard diet. Number of successes was 15. Number of failures, also 15 exactly. Both of these exceed 5. And so now we can say this shows the sample size is large enough. Next thing we would like to address is whether we believe we have a simple random sample or not. And we might say, well, this was a design and controlled experiment. And in an experimental design, you take the initial participants and randomly assign them to 2 different treatments like enhanced or standard, you do get data that are considered a simple random sample. But that reasoning doesn't even work in this problem. It's kind of unfortunate. The reason being is we treated the opossums to these 2 different treatments, but the sample is the 33 offspring from the enhanced diet, the 30 offspring from the standard diet, and we need to determine if those can be considered random data. I would have no clue. This is a very deep question. People who work in biology, who work in opossums, those are the right people to address that kind of question. So in this kind of setting, I would say, provided these data can be considered random, and I'm not too certain on that, the conditions are met. That's one of the things that's a little bit tricky about statistics is sometimes the most important thing you're trying to analyze is if your data is independent, if it's random, but those are extremely deep questions. You have to be an expert in the field, an expert in biology working with opossums to really address that question. So we're outsiders looking in. We'll just try to say what we know about randomization. If we don't find any information, then usually we write down a disclaimer like this. Doesn't mean we stop the procedure. We'll just keep on carrying on. But it might be a good call. Remind me if I forget that when we go to give the practical conclusion, that to say our findings may be challenged if our data is determined not to be random. So that could be a comforting statement to put in at the very end. But we did it, folks. This is the hard part of statistics, in my opinion. Indicating parameters, setting up hypotheses, checking conditions. It's all par for the course, but it's careful work. After we get beyond that, this is the mathy part of everything. Let's calculate the pooled sample proportion of successes, which we call just p hat. So to get that value for p hat, we need to consider these data above. Let me see if I can zoom out just a touch. So what we'll do is, by formula, p hat is the successes in sample 1 added to the successes in sample 2. Pull together your sample sizes. So we'll have 19 plus 15 in the numerator. Divide by 33 plus 30. So altogether, it looks like, let's see, 34 over 63, provided I added those correctly. Does that look right to folks so far? Okay, once we get our p hat, the next thing you'd want to calculate immediately is going to be the standard error. which makes sense because the standard error is based off this p-hat right here. It's not actually based off the sample data that you see here individually. It's based off the pooled data. And the reason for all of that is when we go to get a p-value, we're going to assume that this null hypothesis right here is the fact about the populations. It's essentially a statement that there is no difference between the enhanced and standard, and so we should pool the successes together because we're estimating a common proportion if those are really equal. So next thing we'll calculate is this new thing. It's called SC for standard error of p-hat, but this one is different from chapter 19. I feel like that's a good disclaimer to put right away on this thing. It'll be equal to the square root of p-hat times 1 minus p-hat, multiplying 1 over n1 plus 1 over n2. So let's dump in our data. We get square root. First throw in p-hat, 34/63. 1 minus 34/63 for the 1 minus p-hat. Now we multiply by the sample sizes, and let's see. I'm going to have to take a screenshot of that, I think. Okay, let's just park that there for the moment. So let's take the sample sizes, 1 over 33 for the 1 over n1 portion, then plus 1 over 30 for the 1 over n2 portion. And it's all of that in that format that's going into the calculator. So this is our next step, actually throwing it into the calculator. If we can, nope, we're still going to need that for the next portion. In this calculator here, I'm going to produce SQRT for square root, 34/63 times 1 minus 34/63 times 1 over 33 plus 1 over 30. Let's see here, just making sure my parentheses come out right. And this is the value I'd be getting, 0.125733. Well, we've got the standard error. Any questions, folks, to that step? Okay, so once we produce that, the p-value is not too bad. Well, we still have to calculate test statistic first. So for the test statistic, formula on this one will go z equals, we take the statistics, p-hat 1 minus p-hat 2, and we're not referring to this p-hat any longer. Again, these are pretty confusing problems, so that's why we're going kind of carefully on these. We do divide by the standard error of p-hat from the prior step. But for p-hat 1, we go to the original data, take the 19 successes, divide by the sample size of 33. Subtract for p-hat 2, same idea, 15 successes over a sample size of 30, or just a 0.5 if you prefer. And standard error is the 0.125733. So that'll be our test statistic. At this point, I think we're done with these data here. But any questions at all, folks, on putting it all together on the Z test statistic? Okay, let's now eliminate this since I believe we're done with it and go for this next computation. So we'll need a parenthesis for the numerator to obey those all-important order of operations. 19/33 minus 15/30, division by 0.125733, gives us a test statistic, which is not impressive. That's not even 1 standard deviation away. That's a pretty good indication we're going to fail to reject the null hypothesis. We still want to get a p-value out, so let's record this, 0.6025. And now we're ready for the next step of computing the p-value. To get the p-value, we always want to double check. What was our hypothesis? The alternative is specifically, it was a right tail test because of the greater than. And if it helps out, double check this table here. On the right tail test, you're pretty much just doing this, and that's about it. There's another probability function, just like you did in chapter 11, way couple months back in the course. So our p-value goes like this. We have a right tail test, so it's going to be p norm, throw in your z-test statistic, 0.6025. And that's all you need, except we also have to control lower dot tail, set false. And that's all it'll take for us to get a p-value out of this thing. Let me get extra space here. We're almost ready to get the p-value, so the next place to be looking as well is our original hypotheses, the definition of our parameters, as well as the significance level alpha that was stated. So let's just drop that down there. So returning to the p-value portion, this will be pretty much as it's written out, p norm, 0.6025, lower dot tail, set false. And we get this as our p-value, 0.2734. So we've got it, folks. With that p-value there, we compare it against alpha. This is definitely greater than alpha, which will imply we will fail to reject H naught, meaning we failed to find enough evidence that that alternative is actually true. Putting a red box on it, not to say that's the answer, but more to say, we need to make an interpretation right here. We need to directly address our hypotheses, and then we can answer the larger question of, is the Trivers-Willard hypothesis something that we can detect in this scenario? Doesn't look like it. We failed to reject the null hypothesis, but we have to directly interpret this statement right here that we formed. It could be something along the lines of these data do not, let's highlight, we said do not because of the greater than right here, provide significant statistical evidence let's put the explanation at the 5% significance level. That. Then coming down here, P1 was the proportion of male offspring given the enhanced diet. And we said it should be greater than the proportion of those same male offspring giving a regular diet. So let's see if we can make that one sentence. Take a deep breath and let's say, we failed to provide significant statistical evidence that the proportion of male offspring for opossums given an enhanced diet is larger because we have a greater than there than the proportion for, let's say, proportion of male offspring for the regular diet. I did shorten that up a little bit. I didn't say for opossums given the regular diet. So you're okay to take a little bit of shortcuts there as long as you've conveyed everything you said about the parameters initially, then a little bit of terseness here is okay. So we addressed the hypotheses directly, but the larger question, if we scroll up here for just a moment, was, does this finding provide evidence in support of the Trivers-Willard hypothesis? And we can say, in other words, no. We cannot support the Trivers-Willard hypotheses with these data. The hypotheses might be accurate, but we were not able to detect that difference from the sample data that was provided. Perhaps a larger sample size might have helped. Perhaps giving them an extra enhanced diet might have helped right here. But one thing you could have never done is starve the other opossums, giving them reduced diets and such. Again, that's something that probably would have never passed the ethics board, unless there was a very, very critical reason why you'd be testing that hypothesis. Well, any questions at all, folks, on running through that complete set here? Okay, well, it's another day, another hypothesis test. After you do a lot of these, it does start to feel like it gets redundant after a while, but there's plenty of trickiness still in these kinds of methods because now that we have so many chapters on the table, it's all about choosing the right method once we're confronted with data that's out of context. So I have a document that's going to assist us with that, but I wouldn't say it's the best document. It's not the one I'm going to be using for reviewing for the final exam necessarily, unless anyone wants to solve a question off of there, which I'm absolutely open to. The better document for a review that I'm going to be publishing next on the Moodle website in this week here, April 22nd to 28th, will have, I think, about 6 to 8 statistical problems, but they're all completely randomized. It's going to be up to us to determine what is the right situation, which context are we using to pick the right method. So this is going to be a helpful document when you're doing the real final exam. It's all about determining what the variables are in the problem. For example, if you're dealing with our situation in chapter 20 that we just finished, we have a one categorical variable that decides successes, failures, and another outcome with another categorical variable with exactly 2 outcomes. This is determining 2 independent populations. Then you'd just be going to chapter 20. You would probably just go directly here, open a folder, and you can find all the methods, worked out examples. So Moodle is really, all along, our goal here was just to produce a long list of resources to help us solve these kind of problems. So if we had, for example, 2 independent quantitative variables, we're in chapter 18, but the variables are dependent, we're still in chapter 17, and we didn't have enough time to go through all of the methods I would have liked to. For example, we just ran out of time for, what if you had 3 or more independent quantitative variables? We would have used an analysis of variance in chapter 24. But we only are going to go up to chapter 21, sorry about that. So let's keep on scrolling down through these problems we analyzed. And this is the new situation right here. When you look at these data, it says, well, there's a lot going on, potentially. We wonder, is the data categorical? Is the data quantitative? And that's going to be the very first questions you'd want to ask and answer. Let's read through the context first to see if it helps out. It says automobile insurance is more expensive for teenage drivers than for older drivers. To justify this cost difference, insurance companies claim that younger drivers are more likely to be involved in costly accidents. I would agree with that statement. I was a teenager at one point. So they do have to really justify this. And so to test the claim, a researcher obtains information about registered drivers from the Department of Motor Vehicles, selects a sample of 300 accident reports from the police department, and they go on to say next, the DMV reports the percentage of registered drivers in each age category as follows. 16% are younger than 20, 28% are 20 to 29, 56% of those drivers are age 30 or older. But already, this data looks like it's categorical. What they've done is they've taken 300 accidents and just categorized all 300 by what age the driver was in. Makes sense if they can show that most of those accidents were in a certain age range, for example. So we can say here that variable of the study is age. What kind of variable is it? Well, we've categorized 300 different accidents into this table, so it's categorical. Knowing that's categorical is not enough for us to select a method. We've looked at a couple of categorical variables. ones that involve methods in chapter 19, methods in chapter 22, but these data are entirely new. This is the reason. There are 3 outcomes. Let's list them just because it would be weird not to. The 3 outcomes are under 20. The second outcome is between 20, 29. And the third outcome is 30 or older. So this is the major issue. We have exactly 1 categorical variable with 3 outcomes. Let's put down here exactly 1 categorical variable. We can't analyze it like we did in chapter 19 because there is not a notion of successes and failures, and we're not trying to collapse 2 categories into one and call them failures, for example. We really want to look at all 3 categories simultaneously this time. So there's exactly 1 categorical variable, 3 different outcomes, and we can say here, we will use the chi-squared this is a long statement, goodness of fit procedure. So that's the procedure that helps us analyze these kinds of data. And this is only used if there are more than 2 outcomes and 1 categorical variable. Well, any questions, folks, with the scenario with these data here? Okay, so when you're doing the final exam, you could use this document as just an extra resource. If you see a problem on the final exam where you're just thinking, I'm really not sure what the right method is going to be, scroll through these problems here, and you're probably going to find some data that looks similar or familiar, and that will help you determine where you're looking at. If it says 2 sample methods in chapter 18, then that's a good help. I would say a lot of people, when you open up the final exam, you might really just be up here most of the time, but go down into the document if you need to find further reasons to justify why one method should be used other than another one. And the ones, to me, that are the most tricky are these 2 right here. It's not always easy to tell apart between the dependent and independent variables, but there are examples in this document as well that highlight those differences. Any questions at all, folks, then, before we take a look at that chapter 21 to help analyze these kinds of data? Okay, well, I'll save this up, and I'm going to post this doc. Oh, sorry, go ahead. No worries. Yeah, there'll be exactly 1 question from chapter 21. Yeah. Other questions so far? Okay, and because you mentioned that, let's put something additional on this document. On the real final exam, I'm going to have a question that is 1 quantitative variable. I'm going to have 2 dependent quantitative variables, 2 independent quantitative variables. We're skipping this one for obvious reasons. We didn't cover that material. I'll have 1 like this, 1 like this, and 1 like this. So we're looking at 6 problems exactly, and it's really just up to us to determine which is which, essentially. Let's say check means this is a problem on the final. Any other questions so far, folks? Okay, well, let's take a look at that chapter 21, but maybe even before taking a look at chapter 21, there's another document down below here that says different contexts for P. It's kind of a mysterious title, so let's open it up and take a look through that one. This one's purely informational. It's not going to be updated. It's just going to sit right exactly there as a PDF. But its purpose is, you might have noticed that the symbol P is used in so many different places, it starts to become very hard to tease apart the differences. The symbol P is really highly overloaded in the sense that sometimes it's a P value if it's an uppercase P. So what I have going on in this document is the symbols that you see, the chapters they emerge in, and just quick explanations or fast scenarios to describe how the symbol is used. Chapter 19, lowercase p is the true sample proportion of successes, for example, where p hat is the sample proportion of successes. P tilde is the +4 estimator. We didn't do this problem, so we're not too worried about P star. But then you got P naught from the null hypotheses. P1 and P2 have their own meaning. So the P hat 1, P hat 2, this is all chapter 20 stuff. Now it gets a little bit bizarre because this P hat is specific to what we just did in chapter 20, hypothesis testing. And so it comes into play in this kind of way, where you're adding the successes and failures together. And now in chapter 21, it gets a little bit worse. Yes, chapter 21, we're going to have many different P's because we're looking at more than one category. So our hypotheses start to look like this. And even worse, the subscripting starts to double up. That's not necessarily considered a nice way to write mathematics, but that's now 2 levels of subscripting going on right there. And we need to explain all of those kinds of things. So if it ever becomes just a little bit out of control, you're not sure what the P symbol means, come to this document here and it explains how it's used, where it was found, and that kind of stuff. But now let's take a look at chapter 21. And here's how it starts. Not kind of a friendly start, but I felt like whenever you're doing a new probability model, it's a good idea to just describe it. So think of the first page here as informational. The most important thing is the thing highlighted in yellow right here, but that's only because it's that one statement right there, you obtain your p-values. So we're looking at this chi-squared probability distribution. Its density curve, these things just keep on getting worse and worse. That's worse than the t-distribution, but there's a function there, and it's describing these kinds of curves. Now, the curves here are dependent upon degrees of freedom. I think that's yellow highlight worthy right here, because what is k? And these problems, k is equal to the number of outcomes in the categorical variable. Since this is a chi-squared procedure, and we only use chi-squared if there's 3 or more outcomes, this is a good statement to make right away. K has to be greater than or equal to 3. So after that, here's what the distributions look like. This is if k is equal to 4. So that's 4 outcomes. You get a very skewed to the right distribution for the chi-squared. And that already is kind of unusual. Every other distribution we did always looked like this. A nice symmetric curve. That could have been the normal distribution. It could have been the t-distribution. But the symmetry in the curve was actually extra important. That symmetry allowed us to get confidence intervals really rapidly. We are losing symmetry right away. And so you'll notice on these notes, there is no confidence interval method. All we're describing here is the overall test. We're looking for any difference in the parameter values whatsoever. After you find a difference, you would have to do a follow-up test thereafter to start doing estimates on what is the confidence interval for that parameter and so on. So in chapter 21, our author is only describing the overall hypothesis test. We're looking for any differences amongst the parameters. So it is kind of interesting, however, to know that the number of outcomes increases. So from 4 to 6, the skew is reduced, and increase it more and more, it becomes less and less skewed. Kind of nice, but still doesn't help us out with confidence intervals. It's only going to help us get a p-value. So that's the curve we're going to be working on. And once you get past page 1, this is where the method begins. Let's maybe go to right here. So first part of the definition is just a reminder. You only want to use this method if you have exactly one categorical variable with more than 2 outcomes. So k must be greater than or equal to 3. It's the number of possible outcomes in your single categorical variable. And here are the hypotheses that we're actually going to test. The true population proportion of the ith outcome will be denoted by pi. So if there's, say, 5 outcomes, you will have 5 different parameters. The null hypothesis then looks like this. Your first parameter is equal to some hypothesized value, p1 naught. Your second parameter, p2, is equal to some other hypothesized value, p2 naught, and so on until you get to the last one, pk, which makes sense because there are k outcomes. So that's what the null hypothesis looks like most generically, but we don't always state a hypothesis that way. Sometimes we do state specific parameter values here through here. If we did that, we have the further requirement that p1 naught plus p2 naught plus all the way to the last one, pk naught, those have to sum to exactly 1. A different way the hypothesis could have been written, however, might have been h naught p1 equals p2 equals all the way to the last pk. If your hypotheses are written out in this way, then that equation is still in effect. And notice all I've said here is all parameters are exactly equal. Some of the times that's what chi-squared wants, to see if there's any difference between all the parameters, and your null hypothesis is that everything is equal. Other times in chi-squared, we have a specific value for every single parameter, and so we use this equation here to ensure all those specific values to be tested sum to 1. Up here, here's the additional trick. Let's put here for the notes that if your hypotheses look like this, or said a little bit more briefly, if h naught looks like this, then p naught, we only have to specify one of them, would be 1 over k. So all of these equal 1 over k altogether. The reason for that is, well, if they're all equal, they all have to be equal 1 over k for this equation to sum to exactly 1. You would get k divided by k, adding them all together. So sometimes the null hypothesis looks like that. Other times it looks a little bit more awful, and we'll see both problems on these notes to prepare us for the final. Any questions, folks, with the notes so far on the method? Okay, so our first definition is really more about the expected count. This is similar to chapter 19, where we're not looking for necessarily number of successes and failures in the sample. We're looking for the expected count of outcomes in a certain category. So we write that out as n times pi naught. Sometimes, again, your pi naught is simply 1 over k. Other times, they're all specified as different values. So we'll need that to get our test statistic. And here's how our tests are going to look like. This is our null in its most generic format. We'll test against that statement, HA. Pi is not equal to pi naught for some I. That's a heck of a statement. And if you've taken a lot of mathematics, it might not make you uncomfortable. If you've worked with logic a lot, you're probably okay. But I think for most people, me included, when you read that, you might feel like there's different interpretations to it. It seems kind of vague. It's actually super precise, and we just have to be careful. Let's put a note here that what this really means is that at least one equation, pi is not equal to pi naught. That's the meaning of that statement there for the alternative. And notice that that's the only alternative we test in chi-squared procedure. Kind of weird. Usually putting down the alternative hypothesis is the hardest thing, but it's just the default right here. There's a lot to say as well, though, because if there's a difference, if there's a not equals for at least one I, we're saying at least one equation is untrue. That already implies if this does not add up to the right quantity, Another equation is off because they all have to sum up to exactly one. So if at least one equation is not true, then that means multiple equations are not true as well in this thing. But that's how I would think of this statement just as it's written. At least one of them fails. That's what we're looking for. So the null hypothesis is a statement that there is nothing special happening in this population at all. All the probabilities are equal to the specified amounts. And the alternative says there is at least one difference somewhere, somehow. These tests are frustrating because when you reject the null and conclude that the alternative is true, your conclusion is, well, at least one of those probabilities is not equal to the specified value. And then you stop. The overall test is done. That's uncomfortable because you can't just give that conclusion to, say, a CEO boardroom meeting, a bunch of people trying to analyze something. They're going to ask you which equation is false. But that's the follow-up test. Unfortunately, our book doesn't go too far into that. But if you're curious, there are things that you can look into to analyze which equation was the problem here, get confidence intervals and all those kinds of things. But that's a pretty big rabbit hole for the chi-squared procedure already. We're just going to do the overall test in these notes. So that's what the null alternative looked like. Again, a little bit different from what we've seen before. But any questions so far? Okay, what this might resolve for you as well is something that we've been harping on for quite a while. We've often said confidence intervals are a great way to analyze data because sometimes when you reject the null and you say that an alternative is true, you'd like to give a confidence interval to give even more information. But that's not always easy to do, and this is why hypothesis testing is so important. The overall test right here is the first thing that you have to do before you go into investigating confidence intervals. So just like before, we have to look into the conditions. And for condition one, we have to have a simple random sample from a single population whose categorical variable has more than 2 outcomes. This is not required to state because I'm going to assume if you're using chi-squared, you have already made that determination. So let's put here, not required to check. Well, that's probably a bad way to say it. Not required to comment. Let's say it that way. You will want to check that condition, but that's just you determining if this is the right procedure for your statistical problem. So you wouldn't have to be re-explaining yourself. This is the portion that we do have to work on. So let's say here, carefully check. And report counts. This is us looking to see if our sample size is large enough to get an accurate p-value out. And it says here, this is kind of a confusing statement, no more than 20% of the expected counts are less than 5. So for example, if we have 3 outcomes and the expected counts are 2, 17, 50, we've already got a problem because now a third of the expected counts, 33% roughly, are less than 5. If this is our expected counts, our conditions are already failing right there alone. And it's even a little bit more punishing. If we get anything that's an expected count below 1, then that's an automatic procedure stopping situation right there as well. So we have to satisfy both of these conditions, 1 and 2, simultaneously. And the formula for the expected counts is this right here. The total sample size times pi naught. These are the PIs that it's referring to. So once we do that, we're in great shape. And statement number 4, I put it in the notes only for completeness. I'll put here, not required to check. But let's read through it just to see what they're trying to convey here. The first thing is that, and I think it makes sense to most people, that if you're analyzing a statistical problem, your sample size should change, and that's a requirement for the multinomial setting. Chi-squared procedure is based off the binomial distribution. It's really now a multinomial distribution. And so that's why it has to satisfy these conditions. But that's just a natural statement. Statement two is also a natural statement. In fact, this was a requirement for every procedure we looked into. It just wasn't always stated specifically. Our procedures often say you have a simple random sample, and actually having a simple random sample gives us independence in most situations. That's why the author doesn't always directly state this right here. Now, this is important. If we're dealing with a categorical variable and there's k outcomes, that means every piece of data in your sample has to fit in one of those categories, or else you didn't design the problem well enough. These categories have to be complementary. That means it describes all situations, and mutually exclusive means they don't overlap. But if that ever happened, then it would look like the actual variable in the problem just wasn't even defined well in the first place. So condition 3 is also natural. I think condition 4 is the most important one. And what this is saying is the probability of a given outcome, one observation from the sample size of n, is the same for each observation, but all they're really saying is these values do not change. Those probabilities that we specify stay the same. So this is here again for completeness. If one of those conditions goes awry, you're not in a chi-squared procedure, but I don't have any problems where we're going to really directly attack any of those kind of tricky scenarios. The problems that you'll see in these notes and on the final exam are all directly chi-squared procedures, so you don't have to go through all this information here, just mostly for the sake of the notes. It's a lot of oxygen to describe all these kinds of things, but we're moving on to the good stuff. After you do all the careful work of stating parameters, stating your null alternative, then here's how we calculate the chi-squared test statistic. This looks kind of extreme at first, so let's compare what this looks like against one we did in the past. My goal is to convince you that that's actually a natural formula. It just doesn't look like it at first. Let's go all the way back to chapter 2. In chapter 2, we had to calculate things like this. The variance right here, S squared, we often just use the sample standard deviation, but we still considered this formula for a moment. And when you really look at this formula, the fact that we have the difference from x1 to its mean, and we're squaring it, it means we're looking at a kind of distance, really, every time you calculate the variance. This is measuring the deviation of every piece of data from its mean and squaring that deviation. Now, looking back at our problem, here, what we're measuring, let me click on it first. Here, what we're measuring is the difference between your actual data, what you expect to get when the null hypothesis is true. We're going to square that, so we have a squared deviation. And instead of dividing by a sample size, we'll divide again by the expected count. So we're looking at the difference that this is, the actual observed data, what you expect to get in terms of the expected amount. We're going to square them all out, and this is a type of distance much like the variance was. This is in sigma notation, written most compactly. And notice k is up here in the numerator. So you only do the number of outcomes, and if you expanded it all out, it would look like this. That's the chi-squared test statistic. And I do have a comment on chi-squared alone. Chi-squared is kind of a weird statistic that they operate. Usually when you write out chi, it looks like this. So most people think of chi as that, but that's lowercase chi. And our author decided to use uppercase chi. Uppercase chi looks like this. In other words, it looks just about like an X, except it's not italicized. And if I do italicize it, I can't actually tell you the difference. So that's just a weird symbol there. After getting that out of the way, you will calculate your chi-squared test statistic here. What we compare it against is this. That's lowercase chi-squared, but that's now referring to the probability distribution we saw up above on the notes. You will always have lower dot tail as false. It's not that that's a right tail test, but that's just where you get your p-values from this probability model. And here you put in the test statistic. The degrees of freedom are the number of outcomes reduced by 1, and that finally gets you the p-value. So that's the full method. Any questions at all, folks, on running through those steps there? Okay, let's see if we have time to look at one problem here. We might have a little bit more work to do on Monday to complete both of them, but let's see where we end up on this one. This is a fun problem because we looked at this at, I think, day one of the course. We were not able to analyze these data because we just didn't have the tools to do so at the moment. But now we're in a great position to fully analyze these data, producing a complete analysis. So it says, criminologists have long debated whether there's a relationship between weather conditions and the incidence of violent crime. It's a natural question. And so the author of the article, is there a season for homicide? Classified 1,361 homicides according to their season, resulting in the accompanying data. That means we have a sample size. Let's indicate that right away. N is 1,361 homicides. We have 4 different categories. So that means we have a categorical variable K, where the number of outcomes is 4. That means chi-squared is the appropriate procedure for these kinds of data. And for the practical question, let's say, is there any relationship between season and homicides and I want to add just a little bit more in this area. I don't believe this is national data. I think these 1,361 homicides came from a specific city or a specific state. They just didn't actually say that in this write-up of the problem. And you're never required to look into it and actually buy the article. Usually they're behind a paywall. So I'll just say in this particular area. Next thing we need to define our unknown parameters. But, well, that could be a large amount of writing that you would do here. Or you can write out one sentence. Really, whenever we said respectively, it's because of data like these. There's 4 categories, so there are 4 parameters now. We can say let P1, P2, P3, and P4, so there they all are in a group, denote the true proportion of homicides and now we just list out the categories: winter, spring, summer, and fall, respectively. So we've got it down in just one sentence. That's always a nice deal since that could be a lot of writing right there. Next thing we want to do is state our hypotheses. And looking at this problem, the question was, is there a relationship between season and homicide? They didn't actually give us probabilities to test out at all in this problem. Sometimes they do, like on the next problem we'll take a look at. But in this question, if they're just asking if there's a relationship or not, your null hypothesis will look like this right out of the gate. P1 equals P2 equals P3 equals P4. This is a statement of no relationship whatsoever, and it's natural that that should be the null hypothesis because the research question, is there a relationship? These questions are often the alternative hypothesis that we want to look at. So the opposite of there being a relationship is no relationship. That's just saying all of the population proportions of homicides are equal. But you might want to include one extra thing. If there's 4 of them and they're all equal, they all have to take on the probability of 1/4 exactly. We actually need this because this is the value you need for, let's say needed for checking conditions. We need that to find the actual expected counts. So that's our null hypothesis. Our alternative is always the same thing. It's a statement that at least one of those equations is false, which would then imply 2 of them are false, because if one of them is not 1/4, the others have to adjust. The total of those has to always be exactly 1. So you can write this out in a number of ways. If you like the mathematical way of presenting it, which is up here, pi not equal to pi naught for some I, I'd say that's terrific. It's extremely precise. It's very terse. It gets the meaning across. I'm very happy with that statement. I would say for the notes, though, if I was going to write down an alternative hypothesis that's just a little bit easier to read, I would just write it out this way. At least one equation in the null hypothesis is false. That conveys the exact same meaning that the compact statement would say. So if you're a fan of writing it out like this, I'd say go for it. And if you prefer this, the mathematical way of expressing it, that's just as good. I will just leave it up to you. It's, again, a stylistic choice in the end of the day. So that's what the alternative hypothesis would look like on this thing. It says choose a significance level. Let's leave that up to the class. Any volunteers for a level of significance? Oh yeah, go ahead. Let's go for that, awesome. We will test, let's say, test at a alpha equals 5% significance level. Well, we're nearly done there, folks. We're almost done with the problem, but I want to put something here. Come back. This is more for me, so that I don't forget to check the conditions. We just don't have quite enough time for that. But I want to at least show you how I'd probably analyze these data as they stand. In RStudio, let's save the syntax if you decide to analyze it this way as well. I would first import the counts. Counts gets C to combine 328, 334, 372, 327. And we're using a chi-squared procedure, so you'd probably type chi, and there it is. Chi-squared.test is what we need. Put in counts, and this is a comment I want to put down. This only works when P1 equals P2 equals P3 equals P4 equals 1/4. So in other words, if all of your parameters are set equal to each other, this syntax works just fine. If they are not, we need to specify a new vector to say what all those actual values are going to be. But for these data, this works just fine. If you run that syntax, it says, for the chi-squared test on the given probabilities, the test statistic, uppercase chi-squared, is 4.0345, but we can't think of that in the same way. That's not a number of standard deviations any longer. Degrees of freedom is 3. That sounds correct because we had 4 outcomes. Degrees of freedom is 1 less. And our p-value came out large, 0.2578. So when it comes to actually calculating a chi-squared, it's really pretty rapid. Even if we had a nastier looking null hypothesis, it really just boils down to this. Let's put in that syntax as well. So we're just about done with the problem. We have a very large p-value, and any significance level that we would have picked, we are still going to fail to reject this null hypothesis. Which means when we finalize this problem on Monday, we'll probably say something along the lines of, these sample data do not provide significant statistical evidence that at least one of these equations differs from a fourth. In other words, we did not find a relationship between season and homicide, despite our careful work. And if you remember how that problem worked back in the day, in chapter 1, I think that's kind of a surprise because the display of the chapter 1 shows data that looks like this. It looks like there is a real effect going on in the data, but that's why statistics is so important. We can now say that that bump we see in the data, that looks like it was by randomness alone. There's no real effect actually going on in this population. Maybe there is an effect, but it was so tiny that we could not determine it by the data that was provided. We got a large p-value. Well, we have a couple things to come back to describe the conditions. And I also want to describe what should happen if you have wonky probabilities provided. But any last questions, folks, before we call it a night? Okay, this will be our stopping point then for today. On Monday's class next week, we'll finish off this and then launch right into reviewing for the final exam. So I'll have new problems and such posted there. Well, have a great night, folks, and I'll see you all next week. Take care, folks.